Welcome to my video course on mastering ERTMS/ETCS signaling systems. Today, we're diving deep into one of the absolute most fascinating engineering marvels in the modern transportation world. We're talking about the digital backbone that keeps high-speed trains safely hurtling across continents at 300 kilometers per hour. If you've ever wondered how thousands of tons of metal can be orchestrated perfectly across borders without a single physical traffic light in sight, well, you're in the right place. We're going to break down this massive architecture step by step. Here's our roadmap for today. First, an introduction to ERTMS. Second, ETCS command and control. Third, ETCS levels explained. Fourth, GSM-R railway communications. And finally, the traffic management system. Let's get right into it. Section 1, Introduction to ERTMS. ERTMS stands for the European Railway Traffic Management System. Now, the absolute key phrase I want you to remember here is interoperable platform. For a long time, railways were strictly national affairs. But as trade and travel exploded, the total lack of a standardized international system became a huge bottleneck. So ERTMS is the standard program designed to unify railway signaling and authority across the board. It basically ensures that a train starting in Italy can seamlessly cross into France, Germany, and beyond without having to change locomotives or swap out drivers. The historical fragmentation of European railway signaling systems used to be intense. We're talking about AWS in the UK, TVM in France, Indusuni in Germany, ASFA in Spain. It was literally a patchwork of completely incompatible national systems. Before ERTMS, a cross-border journey was an absolute logistical nightmare. Trains actually had to stop at borders to swap out equipment or even change entire locomotives just to be able to read the local track signals. It was incredibly inefficient. To solve that nightmare, engineers came up with what I like to call the ERTMS equation. I want you to hold this simple mental model in your head. ERTMS is essentially made up of two distinct but perfectly integrated halves. On one side, you've got ETCS, which is the signaling logic, basically the brain of the operation. And on the other side, you have GSM-R, which is the dedicated mobile communication network, the nervous system. Put them together, and you've got the ERTMS platform. Section 2. ETCS, Command and Control. ETCS, or the European Train Control System, is essentially a highly advanced automatic train protection and control system. But the real magic here, it's the shift to cab signaling. Instead of a driver looking out the window trying to spot physical colored light lamps bolted to the side of the track, all of those safety and movement authorities are transmitted digitally. They're displayed right on a screen inside the driver's cabin. It literally brings the external infrastructure directly inside the vehicle. Now, for ETCS to pull off this digital cab signaling, its physical architecture is split into two main subsystems. You have the trackside subsystem, that's all the hardware bolted to the ground, and the train-borne subsystem, which is the hardware riding along inside the locomotive. For the whole thing to work, these two sides have to communicate flawlessly in real time. Let's look at what actually lives on the trackside. First, you have the RBC, the Radio Block Center. This is the heart of the trackside system. It securely manages the separation between all the trains in its assigned area. Next are Eurobalises. Think of these as smart track magnets placed right between the rails. They send precise location and route data up to the train as it passes over them. Then there's the NTG, or Network Transmission Gateway, which acts as the interface translating data into radio signals. And finally, the KMS, the Key Management System, which handles the cryptographic keys to make sure hackers can't intercept or spoof the train signals. Take a second to let those acronyms sink in. Especially the RBC, it's really the traffic cop on the ground. Hopping aboard the train itself, we hit the train-borne components. The big boss here is the OBU, the onboard unit. This is the train's central signaling computer that crunches all that incoming data. That data is then visually presented to the human operator through the DMI, the driver-machine interface, basically a high-tech cockpit monitor. And underneath the train, you've got the Eurobalise antenna, which magnetically picks up the spot data from those track magnets we just talked about. Section 3. ETCS Levels Explained. It's really fascinating to trace the technological evolution of these ETCS levels. We start at level 0. This happens when an ultra-modern ETCS train finds itself driving on an older, non-ETCS route. The onboard computer basically just acts as a speed limiter, while the driver relies entirely on old-school trackside visual signals. Next is level 1, which is kind of a stepping stone. Here, ETCS cab signaling is superimposed on top of fixed trackside signals. The train updates its permissions by running over those Eurobalise track magnets in what's called semi-spot transmission. But the Holy Grail? That's level 2. In level 2, physical trackside lamps are removed entirely. It relies on digital, radio-based virtual signals and a continuous, unbroken stream of wireless communication. Let's really emphasize this because it is the absolute core of modern high-speed rail. In level 2, the train and the radio block center are constantly talking. The train is continuously reporting its exact speed, position, and direction. In return, the RBC dynamically sends back movement authorities. These are essentially digital green lights telling the train exactly how far and how fast it is allowed to proceed. But how is that data actually used to keep everyone safe? Well, it all comes down to dynamic speed monitoring. The onboard unit takes that movement authority from the RBC and calculates a specific protection curve tailored exactly to that train's braking capabilities. It knows exactly when the train needs to start slowing down to hit a target speed or come to a complete stop. If the human driver makes an error and the train speed exceeds this calculated protection curve, the ETCS system immediately takes over and automatically applies the emergency brakes. It's an incredibly robust, mathematically precise safety net. Section 4. GSM-R Railway Communications. GSM-R stands for Global System for Mobile Communications, Railway. Now, it's absolutely crucial to understand that this is not the public 4G or 5G network you use on your smartphone. Not at all. GSM-R is a dedicated, highly secure, closed mobile communications network used exclusively by the railway sector. It handles all the data telegrams between the trackside and the train, plus the voice communications for the ground staff and drivers. To guarantee that this closed network is never interrupted by civilian traffic or outside interference, GSM-R operates on a specific reserved frequency block in the 900 MHz band across all of Europe. By carving out this exclusive slice of the radio spectrum, railway operators can ensure the safe, uninterrupted, high-priority transmission of those vital braking and movement commands. The actual network architecture looks quite a bit like a traditional mobile telecom setup. You have the RBC generating the signaling data. That data flows through the ISDN network into mobile switching centers, then out to the base station controllers, and finally gets broadcast via antenna towers directly to the speeding locomotive. It's an incredibly robust chain of communication designed for maximum reliability. But as incredible as GSM-R is today, we always have to look toward the future. Current GSM-R is circuit switched. That means it reserves a full dedicated radio channel for an entire connection, even when no data is actively being sent. On highly congested railway lines with lots of ETCS Level 2 trains, you actually risk running out of channels and causing a system deadlock. The future evolution is GPRSR, which is packet switched. Just like modern internet protocols, it only uses bandwidth at the exact microsecond a data packet is being transmitted. This is highly efficient and is going to allow vastly more trains to operate on the exact same stretch of tracks safely. Section 5. Traffic Management System, or TMS. This brings us to the Traffic Management System, or TMS, sometimes also called ATS. If ETCS is the reflexes and GSM-R is the nervous system, the TMS is the macroscopic brain overseeing the entire physical and digital railway network. It sits right above the individual trackside components and provides a complete bird's-eye view of the entire operation. The core functions of the TMS are incredibly vast. It takes all the raw data streaming in from the ETCS and GSM-R networks and uses it to plan, regulate, and optimize train traffic. It looks at the real-time state of the infrastructure, like knowing instantly if a track circuit is occupied or if a switch is stuck. Crucially, it also performs constant diagnostics on all the equipment, instantly alerting operators if an RBC or an interlocking mechanism starts reporting faults. It's constantly optimizing the overall flow of dozens or even hundreds of trains simultaneously. And despite all of this brilliant automation and algorithmic safety, humans are still firmly in the loop. The real genius of the TMS is that it consolidates millions of complex data points onto a single intuitive human-machine interface. This allows human operators at traffic control centers to easily supervise the network, make strategic routing decisions during delays, and maintain total situational awareness over the entire railway system. As we wrap up this deep dive into the ERTMS architecture, I want to leave you with a thought-provoking question to ponder. As European rail traffic continues to surge, and we make that necessary shift from circuit-switched GSM-R to highly efficient packet-switched GPRSR networks, how else do you think the physical and digital architecture of ERTMS will need to evolve? How will it handle these incredibly dense traffic loads without compromising that perfect safety record? It's a really exciting frontier for railway engineering. Thanks, we can see in next video.